Today we're going to be hearing from David, Emmanuel, and Julius, who I believe are all at the University of Munich. Um, and they're going to be telling us about some stuff to do with sampling from Bayesian neural networks. Take it away.
Thank you very much for the introduction and also for inviting us. Yeah, so as Rowan said, I will give or we will give a talk about the lessons from sampling Bayesian neural networks. This is Julius and Emanuel, who are PhD students in my group, and I'm a professor of data science at LMU Munich. This talk is also based on collaborations, contributions from a couple of other people. Now I think you need to change the slides, guys, because we're sharing like they share the slides. So yeah, great. Contributions from other people, so other co-supervised PhD students in particular, Daniel and Lisa. And so when we talk about sampling in Bayesian neural networks, and we talk to people in the community, usually there's some common perception like that, well, why do we do this in the first place? There's no meaningful queries in weight space, so why do you want to do sampling? It's also too expensive. You can only do this for small scale, and it is impractical due to all of these symmetries that we have in the landscape. And in this talk, we sort of try to challenge all of these points. We do that by I start with giving a short introduction, which also is a bit unconventional. It will show some results already, and then we get to the ingredients for like the results are successful. They show that we can successfully sample Bayesian neural networks, and then Emmanuel and Julius will dive into the ingredients for this success, in particular overparameterization and sampling. And then later on, I will then talk about some of the implications. What does that mean if we are now able to sample from these neural networks, and I'll give some outlook. What are the current bottlenecks and some summary. All right. Then let's start with the introduction. Yeah. As I said, like I will start with some results, and you don't need to read every number here. The point is more that so we have like the typical small scale benchmark that you see when talking about sample-based inference. There's some LPPD and RMSE values in the different rows for four data sets. We have the Laplace approximation method, mean field variation inference, and a deep ensemble with 10 members. And so we look at both the log pointwise predictive density and the root mean squared error. And sometimes deep ensemble is better than the others. Sometimes the Laplace actually is also outperforming the deep ensemble. Now, if you take the deep ensemble and you add something to it, you add sampling to it, which is the last column here. So you run 10 members of your deep ensemble, and then from these final solutions, you start sampling. You see that you actually gain a lot by this. You can already tell by the signs of the LPVD, but also you see, for example, if you look into the fifth row airfoil RMSE, you can almost half you get half the size, half the RMSE from what you got from the deep ensemble. Then you might argue, well, this is just due to like you have the deep ensemble already, and then you add sampling, so it's not surprising that you improve. But if you look into just sampling, which is the column with most of the blue values, then you see that actually all the values are blue if they are better than the deep ensemble. You see that in most cases you improve over a deep ensemble, which means that, well, while the deep ensemble is exploring the space and trying to find different solutions, the sampling starts in one place and tries to exploit the vinicity of this space. And that already improves in the two metrics. So there seems to be something to sampling that helps you understand the neural loss landscape or the posterior, where it's definitely worth into looking into, well, also your neighborhood, and not just well, trying to find as many different solutions as possible, like the deep ensemble does. Yeah, so you might argue now that this is just for small scale, but actually we have lots of results also for larger scale. Here you can see a similar picture. In the third column, there's the deep ensemble with now 12 members. Um, right to it is the Bayesian deep ensemble, which is essentially what we showed before. It's deep ensemble, and then from every of the, in this case, 12 members, you start sampling, and then you try and you improve by well, sampling in the surrounding of these 12 solutions. And again, like before, you can see that so now for larger data sets and larger architectures, we even have yeah more large scale results for this now also. Again, like before, you see that the average chain, which are the blue values, meaning that you pick one of these 12 chains, they are better in performance than the deep ensemble in I think in most cases at least. So sampling already improves over just taking different map solutions. You could see them as map solutions maybe. But then in contrast, if you take the average deep neural network DNN performance of like one of these 12, like you have these 12 solutions from the deep ensemble and you take the average, then this does not perform that well. So it's again, maybe there's something to sampling that can help us at least improve the prediction performance. Yeah, and so the in both of these examples, you might still argue that this is an unfair comparison. Sampling gets more budget, right? So we sample. There's usually the question how much do you sample? That very much depends on well the use case. But so you can try to make a fair comparison. This is what we did here. We have on the left y-axis the runtime and the right y-axis the LPVD again. And then you can maybe focus on the two bar plot pairs, the deep ensemble 35 and the BDE 1, which is essentially the comparison between a sampling approach that only uses one chain and samples, and then the deep ensemble with 35 members. And you see that the blue bar plots are almost the same. The two blue bars in terms of LPBD, meaning that these are models that perform roughly the same. But then you see that the runtime for the Bayesian deep ensemble, meaning in this case Bayesian deep ensemble with one member, is just one chain that you sample with one chain. This is actually faster than the deep ensemble, and while being in terms of performance being the same as these 35 members of a deep ensemble. So actually, the runtime is not, or the budget is not more than for these conventional methods like deep ensemble. And this is also something that we definitely want to highlight with the software that we have and the methodology that Emanuel will present later. We're in a ballpark where sampling is now I think quite doable. So on the next slide, you will see that there's some wall clock runtimes for different data sets in the different rows. And we have the deep ensemble runtimes here in the first column. So for example, for B, that's the bike sharing data set, it takes 5 minutes. For P, that's protein data set, it takes 12 minutes to get the deep ensemble solutions. In this case, I think it's 10 or 12 chains, again, 10 or 12 members. And then the perception that sampling is slow, well, there's a reason that there's this perception, because if you then would add nuts, for example, on top, so a no U-turn sampler, it takes, for example, for protein, in addition, 2.5 hours to sample from the Bayesian neural network, which is notably much more than these 12 minutes that it takes for the deep ensemble, or 48 minutes for bike sharing. But then if you take another sampler, which is something that Emanuel will present later, which is the plus hours column, then sampling actually is roughly the same in terms of time than the optimization that we did for the deep ensemble. So you can see, for example, in the row with the B, the bike sharing row, it's 5 minutes for getting the deep ensemble solution and 5 minutes for then doing the sampling. So it's something that I think we would all be willing to invest if it's roughly the same, requires the same amount of time for doing optimization and then for doing the sampling. Then this is something I think this is practically now relevant, and then people would be willing to look into sampling maybe more. This is something that we definitely want to highlight here in this talk, that it's now practically feasible in the sense that people would be willing to invest the budget. Next slide maybe. And
so
so
maybe
please, Julius.
Yeah, so maybe after just seeing all these results already, we take a step back and try to define the ingredients for the success that we have seen. So first, let me quickly go over the setup of this talk. So we've now seen some results. Let's clarify what setup we're in first. So in most cases, we're concerned with full batch sampling. There also exist stochastic MCMC variants, as I'm sure you know from, for instance, SGLD. Of the estimation of the local learning coefficient, for instance. But our case here will mostly concern full batch sampling. And our general setup is that we view weights and biases of neural networks as random variables that follow a distribution. And then we pick a likelihood, for instance, a Gaussian likelihood for a regression task, and try to sample this unnormalized log posterior using sampling methods, MCMC methods in our case. What is interesting is that we also, in this Bayesian framework, we also need priors. And like in classical Bayesian statistics, we define these priors in weight space. And there's a debate in the Bayesian deep learning community on what these priors actually mean or whether they're meaningful at all. So there are people that say that they can hardly be meaningful because we are walking around in this very high dimensional parameter space. We also have identifiability issues of the network. And then there are other people that say that there might exist meaningful priors. So they mostly look at empirical weight distributions of different networks, or for instance, take into account spatial correlations at BNNs and try to define prior space off on that. But our perspective that we want to share here is that we actually do know something about the distribution of the weights, that we do have some prior knowledge, specifically in the case of overparameterization. And this is why the first ingredient of success that we want to cover in this talk is exactly that, so overparameterization. So let's maybe start with a small toy example. So this is just here to showcase the effect of network-induced regularization if we apply an isotropic Gaussian prior, so a normal prior, which is equivalent to L2 regularization. So you can see 3 columns here. In the left column, you have a very simple 1-1 network, which just means we have one input, then we have one weight that connects this to one output neuron. In the middle, we have an L-layer deep linear network, again without activation, where we have hidden layers that just consist of one neuron, and we have L layers of these, so a 1-1-1-1-1 network. And on the right side, we have a 1M1 network, which just means that we have a hidden layer that contains M hidden neurons. And if we look at the definition for the first network, so the 1-1 network, we see that this is just given by our input that is multiplied with the weight that connects the 2 neurons, or the input and the output neuron. And we can clearly see that the hypothesis space of this model is the space of the linear models. And as we apply our normal prior or L2 regularization, the regularization that is induced is equivalent to the one that we see in parameter space. But this already changes as we move over to the second example. So in this case, we are again not leaving the hypothesis space of linear models because we just now take the product over L of these weights, and we can redefine this to be another scaling factor beta in this case. So we're still in the case of linear models. And if we write down the L2 regularization for this case, and look at the induced regularization on the slope of the function that we get, we have a potentially non-convex penalty, which is this 2 over L penalty on the slope beta. And the same thing occurs or like a similar thing occurs if we look at the 1M1 network. Here, the definition of the function is just given by x times the sum over the products of the in and outcoming neurons of these hidden neurons in our hidden layer, which we define to be alpha. We're still in the hypothesis space of linear models, as this is just, like before, just the scaling of an input. And if we write down our regularization, then we find out that the induced regularization of this network is a lesser regularization on the slope of the function. Let's define now a true model and look at the optimal weights as we increase the number of parameters or layers in this case. So in this first example, we again take the L layer deep linear network and define the true model to be f of x equals gamma x with gamma equaling 2. And if we now let the number of parameters go to infinity, we expect an equal attribution to every weight. So in the limit, every weight should approach 1. This is what you can see here. So we just have for the L equals 1 case, our W1 will just be gamma, so 2. And if we move, for instance, to the L equals 2 case, then we have 2 to the power square root of 2, and so on and so forth. So in the limit, as we increase the number of parameters towards infinity, we get a limiting case where we expect equal attribution across the parameters and the WLs to be equal to 1. But as we've seen before, the induced regularization in this case forces the weights towards 0, or the slope of the function towards 0. So there's some kind of mismatch here. But if we instead look at the 1M1 example, we now observe that we have a sum in our functional definition, in our function definition. And what this leads to is that in the limit, as we increase the number of parameters, again, in this case, the number of hidden neurons, each and every weight will go towards 0. And this is actually this time congruent with the penalty, so the induced penalty. So the lessons learned from this small toy example is that networks that can be over-parameterized while adhering to the penalty and not losing expressivity, which is also important, but we will not focus on this in this talk very much, allow an increasing shrinkage of weights to 0. And in Bayesian terms, this would be equivalent to an increased prior conformity. And what this looks like in a sampling application is what you will see on the next slide. So here we have sampled this very simple toy problem, the 1M1 network, where we can see on the x-axis and the y-axis 2 weights of a neuron, the incoming outcoming weight. And in the m equals 1 case, depicted here in blue, you can see that our sampler recovers exactly all parameter combinations that lie on this banana. So if you multiply the weights that lie on this banana, you get 2, which is actually the true function you want to approximate. But as you increase the number of hidden neurons, so m in this case, we turn towards these red points, which are now much more centered around 0, as we have expected from our toy model analysis beforehand. And interestingly, this phenomenon is not just limited to toy examples like the 1M1 network in this case, but we also see it in real-world scenarios, for instance, in larger radio networks that are actually used for regression on a UCI dataset. So on the left side, you can see, so again, what you can see here is our marginal plots. So what we do is on the x and y axis, we pick a certain weight, or not really a certain weight, doesn't really matter what weight you pick, but we fix a certain weight. And then we marginalize over all the other dimensions of the parameter space to produce these plots. And on the left side, you can see an under-parameterized network, while on the right side, you see an over-parameterized network. And interestingly, On the left side, you see these gaps here, basically, that if they're there in the marginal view, then they must also be there in the joint view. We have this disconnectedness going on, while on the right side, the model clearly has enough capacity to adhere to the prior while we do the sampling. So we get this nice looking fireball plot, basically, where we have this marginal prior conformity that again shows up also in these examples. Sorry. There also exist similar results in optimization that connect nicely to this finding. So for instance, there's a paper by Kim, Mishkin, and Palanchi that was published this year, where they look at a two-layer ReLU network from a theoretical perspective and try to try to find out what the set of solutions of this regularized two-layer ReLU network looks like. And as you increase the number of hidden neurons, so the number of neurons in the hidden layer, which is called M in this case, you first start off with disconnected solutions that are depicted in red. Once you have this first, then you have this first phase transition where you get some solution sets that are connected to each other, which are depicted by these blue areas. And once you increase the number of hidden neurons enough, this interestingly depends also on the number of observations, you get just one collected set of solutions where you can interpolate between the optimal parameters freely while only incurring minimal loss. This is another example of what this looks like in our sampling case. So if you look at the marginal posterior densities of the product of an incoming and outgoing weight of a neuron in a ReLU network, this is again on a UCI data task. You see on the left that in the case of an under-parameterized network, we have severe multimodality going on. The distributions are not really centered around zero. While on the right side, once we increase the number of parameters in this network, we get distributions that are centered around zero and look nice, much more well-behaved. And this is basically telling us that the network is kind of splitting the feature extraction equally among all the neurons. And there's a similar result that was analyzed in variation inference a couple of years ago, which is called variational overpruning. And that's an interesting phenomenon where they basically try to approximate the posterior distribution of a neural network using a mean field surrogate posterior, which just means that the parameters are assumed to be independent. And interestingly, what they found in this paper is that if you use this kind of approximation method and you use complex models, they tend to perform worse due to a phenomenon they call pruning, which just means that most of the learned posterior distributions for the weights and biases just stick to the prior distribution and do not really move, which means no real learning takes place. And in the limit, this induces the conditional independence between weights and data. So also in our case, you could ask yourself, is this actually harmful for our use case or for sampling? And our answer would be that it's not, because we are actually not in this data independent regime, because as we look at, for instance, correlation matrices of our samples that we obtain by sampling, I hope you can see this kind of well. So there is not so much yellow here as you would expect, or as you would if you look at this and you look at it a little bit longer, you see that there's actually lots of structure in these correlation matrices. So if we were in the data independent regime, we would expect the correlation matrices to be diagonal, which is clearly not the case. We have lots of correlations going on between these weights that are recovered by our sampling procedure. So the question now is, so these results kind of suggest that overparameterization pushes the posterior much closer to the prior and also makes the posterior more well-behaved for sampling applications. And as long as the function that we try to model or the neural network becomes more flexible, this might be in our favor. We put two question marks here for this statement, also the following statement, because this is maybe still a little bit up to debate, but we also expect there to be a trade-off between smoothness and dimensionality, as we have also seen in the marginal view of the posterior in these ReLU networks, for instance. And now I've talked about, basically I started my section with saying that we want to sample from a possibly million-dimensional parameter space for these two networks. And now I'm telling you that over-parameterization might be a very good idea, even on top, so that increases the parameter count even more. So the question actually arises, how we are actually able to sample from this parameter space, and if so, and how this works. And this is what Emanuel is going to tell you now.
Yeah, thanks a lot. I hope you can still hear me. Perfect. Then I will take it from here. So the next ingredient for success should be the sampling. It should appear somewhere, I guess. Given the outline trade-off between over-parameterization, which seems to be kind of beneficial considering symmetries, and dimensionality, which is then often considered to be the major bottleneck in effective sampling, we want to discuss this very high dimensional sampling. So we consider for now first, as always, a small toy example to actually look at the problem and develop some understanding. So more specifically, we now consider the zero-centered multivariate Gaussian as our target distribution. Let's just assume this nice parametric form is our target posterior. And when sampling, we care about integration. And in the integration, we want to cover these highest posterior mass areas in the parameter space. And defining a radius now from this zero-center target allows us to actually look at the posterior mass in an, I would say, unusual way. So let's look at the total posterior mass up to a constant, which we can write as a product of the first term, which is e to the power of minus r squared divided by 2, which is the radial density at radius r, and the infinitesimal volume of this thin shell at r. And we can basically decompose these into two functions. As I said, the first one is the radial density of the Gaussian, second one is the volume of this thin shell at radius r. And now, notably, if we look at these two terms, the one term, which is the radial density, does not depend on the dimension, but the volume element depends exponentially even on the dimension. And if we look at this also empirically for some examples, we can have a look at the overall density. So the blue thing is the region we want to sample from. So this is the product, this is the total posterior mass, where the mass of the posterior actually lies. The radial density does not change, which is displayed in red, but given a change in the dimensions, obviously, as you have seen the formula just a second ago, you see that with growing the volume is basically pulling away the total mass area of the posterior from the origin. Right? So we can see that this region where we want our sampler to explore the parameter space actually changes in terms of the dimension. And if we then look at this from another angle, so from these contour lines, we see that most probability mass is located on this, in the picture in purple, in this thin shell at radius roughly at square root of d. So if you also check back with this plot, square root of d should be roughly the center of the blue bell-shaped curve, right, for dimension d. And so we want our sampler to concentrate all the exploration on this narrow, thin shell, this purple shell, such that it is effective in traversing our posterior. And if we now consider one of the most simple samplers that we can think of, which would be the random walk Metropolis Hastings, we can already see why these classical samplers actually exhibit the curse of dimensionality. Because if we now look at random walk Metropolis Hastings, you can think of it as like a random proposal around the current trajectory. If we already start the sampler perfectly on this thin shell, even then, most of the samples that will be created from this uninformed proposal will be rejected due to the Metropolis Hastings adjustment, especially in high dimensions, because this shell will be thinner and thinner, and most of the samples will not contribute meaningfully to the posterior mass, to this integral that we actually want to approximate. So we highlighted this curse of dimensionality, and to tackle this, researchers have actually explored gradient-based sampling as you already might know, and most prominently HMC was introduced. So let's talk about HMC. I guess the details are not super central here, but I'll try to sketch the main idea just to get everyone on board. So HMC not only has the parameter vector, so the position, but also introduced an auxiliary momentum variable pi. Interestingly, this mass matrix here, M preconditions the space. You can think of this as preconditioning also for optimization, and basically allows different velocities in different dimensionalities. And in most cases, practically, this is assumed to be a diagonal-only matrix. And then one can define the Hamiltonian system, which is comprised of basically two terms. It has a drift term, and it has the term with the momenta on the left. And these Hamiltonian dynamics basically come from physics. But now what we want to modulate is the potential energy is derived by the unnormalized log posterior, and our positions are basically the particle, the parameters that move through parameter space. And here on the right hand side, on the right side of the differential equation, you can also see where the log unnormalized posterior and that its gradient comes into play. And this guidance allows to keep the trajectories close to this thin shell, and this then will boost acceptance probability. So what we basically do in practice is we use these differential equations, we numerically integrate them with a couple of numbers of leapfrog steps. We simulate the discrete dynamics for L many steps, and then we have a new proposal just in random walk metropolis hastings, and we accept or reject in the same manner. And as I said, this drift term then ensures that the acceptance probability is much higher. But this is not the end of the story, because there are three key hyperparameters, and these are mostly connected to the numerical integration, but also kind of to the conditioning. So the first two, the step size and the number of integration steps, L, these are the most difficult to tune, because especially if you have very small epsilon, you're very slow but accurate. If it's too high, you diverge. For large L, you get better mixing, but you get the risk of trajectory reversal, which basically means that you integrate you do the numerical integration for L many steps, and you basically return to the position you started off with, which is, of course, not what you want, because this is especially inefficient. You wasted a lot of compute and did not go anywhere. And poorly chosen M basically leads to inefficient exploration in this anisotropic posterior. So if it's very ill-conditioned local neighborhood where the trajectory actually flows. So these are the tuning parameters, but also nicely some researchers came up with nuts, which basically solves a lot of these problems in combination with some other innovations. But the solution is to most of these cases the no U-turn sampler. And the no U-turn sampler, before diving into what it actually does, is considered to be the MCMC algorithm that theoretically scales to high dimensions. So you see a lot of famous names here from a very recent paper from 2024 from the sampling community, and this is basically the state of the art in high dimensional sampling. But how do they do this? So first, what does NUTS actually tackle? It tackles the trajectory length choice. So the L, how many numerical integration steps, how many steps should we actually integrate and develop our dynamics? And how do they do this? They've expanded binary tree of these leapfrog steps forward and backwards in time. We should now note each of these leapfrog steps takes one gradient evaluation, which is already quite costly. And then it monitors on the fly the no U-turn condition and basically ensures that sampling is more efficient. And also it stops when further movement would reverse the direction. I should also note there are also these other two hyperparameters, the mass matrix and the step size. And what is often done is you use a window adaptation scheme during the warm-up. There's a really good one proposed by the people at the STAN, which probably most of you know. And so basically, in the end, you end up with an algorithm that is practically tuning free. So you basically tune all of the different hyperparameters of HMC. But what is actually a bottleneck is that, especially for nuts, this unpredictability of the number of steps that are taken, the integration steps, you don't know how many gradient evaluations you need in advance. And this binary tree even can grow exponentially large. And it grows exponentially large, especially in these pathological cases where it does not perform well, which is kind of, Andrew Gallman once mentioned this in his blog, which is kind of the worst thing you would want. So it spends more compute when it actually shouldn't. So in practical applications in blackjacks, numpyro, pyro, almost always D, the depth of the tree is set to a maximum of 10, such that the maximum number of gradient evaluations per proposal are limited to 1023. So this is basically how it is done in practice. And let's have a look at how this actually looks for some examples. So again, looking at some examples from the UCI benchmark dataset, and we now portray how many gradient evaluations you actually need per chain to generate 1,000 well-performing posterior samples. And let's now not consider mile, which you can think of as a baseline, the orange one, which is maybe a number of gradient evaluations that you might be willing to offer to actually generate these posterior samples. But let's focus on BDE. In this case, the blue boxes are nuts-based, and you can see that for generating these 1,000 posterior samples, the number of gradient evaluations varies a lot, both across and within task. So you basically cannot know before how much time your sample will actually need, which is very tedious in practice because the practitioner then doesn't know how long he has to wait. And these are not small differences. For instance, you can see these error bars within the task. And for some of these applications, differences are 300,000 gradient evaluations. And we know that for Bayesian deep learning, the calculation of the gradient, the forward-backward pass, actually is the most costly thing in the whole sampling procedure. Then it's obvious that this is quite inefficient in practice. And especially if you want to do parallel load balancing of your compute resources, let's say you want to have 10 parallel chains, then always the longest take, the quickest chain has to wait for the longest chain. So, and if this is 300,000 gradient evaluations, the load balancing is really off, right? So this is not something we want to have. So taking this from there, we wanted to change this unpredictable behavior and introduced basically to address this, we want to now introduce the ingredient that was the most important thing for us to address this particular issue. And this is MCLMC, so microcanonical Najm Monte-Carlo, which was proposed in 2024 by two of our collaborators, Jakob and Uroš. Both of them are at the physics department at UC Berkeley. And MCLMC is based on MC-HMC, which is microcanonical HMC, which they proposed 1 year earlier. And this was published in JMLR, 2023. And so basically, what is this MCLMC all about? Let's have a look at the difference between HMC and MC-HMC. So let's just look at the joint distribution of our theta and our momenta pi. And we know that for HMC, this is proportional to e to the power of minus the Hamiltonian. And now for MC-HMC, the joint distribution is different. It's actually a Dirac delta distribution on the energy level set. So it's a Dirac delta distribution of the Hamiltonian being exactly equal to this energy level set. So you can think of it in the right illustration, it basically is always 1 and uniformly distributed with a Haar measure on the ellipsis on this one contour line, which is the energy level set E, and 0 everywhere else. Okay, so basically it's a different target distribution, but the marginal, which is the thing we're actually interested in, the marginal with respect to theta, is the same. And how do we get there? We actually have to modify the differential equations that are used for HMC. So these are the ones that you've seen before. and we need to add something. We need to add a projection step onto the hypersphere. So basically the gradient is the gradient of anomalous log posterior is projected onto the hypersphere perpendicular to the momentum. And this way the energy is always conserved. So this is the first thing, but this is only MCHMC. And this already works. And it is proven to go to the right stationary distribution. But I told you we are actually using MCLMC, which also includes some Langevin type of diffusion. And this is added here to the gradient. So you add a diffusion term parameterized by some hyperparameter eta, and W is a Wiener process. So this is a typical Langevin type diffusion term that is added to the differential equation. And this thing then is integrated via, for instance, min-norm integration, mostly not leapfrog integration, but you can use any integrator you basically want. So given that this is the difference between HMC and MCHMC, why should we actually consider MCHMC? There are a couple of advantages that I would like to point out. So first of all, HMC needs full momentum resampling to actually reach the stationary distribution in theory. As you've seen before, this resampling is not necessary for MCLMC to actually reach the correct stationary distribution. So in a way, it's more deterministic dynamic. So this full momentum resampling is not required, but possible. Then usually no metropolis adjustment is needed because there are other mechanisms that are proposed in combination with MCLMC that actually control the step size and therefore also the discretization error that you want to tackle with metropolis adjustment. But actually it's possible. So there's also MAMS, which is metropolis adjusted microcanonical sampling. So if you're actually interested in the adjusted sampler, it's, I guess, maybe 20-30% slower due to the adjustment, but it also works for MCLMC. This is quite recent work. The preprint is definitely out there already, but I'm pretty sure the main paper will be published, I guess, in a month or so. Well, in terms of gradient evaluations, due to the different integration schemes, NUTS has this varying number, the MCLMC is just deterministic. And what's pretty interesting that under certain conditions and under certain assumptions, it's even provably much more efficient than HMC. So looking at the effective sample size, one can even show, as I said, under certain assumptions, that the effective sample size is independent of the number of dimensions, so constant. And this is a very strong statement. So basically that this says that under certain assumptions, this sampler does not, it's basically not vulnerable to the curse of dimensionality in sampling. And as you might have guessed already, MILE is basically MCLMC based, what we have seen before. So it is deterministic in the amount of gradient evaluations. And what I should say here, it's not only, as you can obviously see from the number of gradient evaluations that are needed, much faster than NUTS. And this is also from the one table that David showed before. But also, if we think about these 1,000 posterior samples that were generated, the downstream performance was always as good as the NUTS-based alternative, or even better in most cases. This shows that it really matters which sampler you need. But the sampler is not enough. So we now covered basically sampling, effective sampling in high dimensions. Well, the BDE does not only incur a really efficient sampler, but also optimization remains a vital ingredient. And we talked before about BDEs and MILE, and basically the two are pretty simple and pretty similar. So BDE is just a deep ensemble plus NUTS. MILE is also, again, deep ensemble based and adds MCLMC in terms of sampling. Why is that interesting? Because this combination gives you a really nice and especially efficient exploration-exploitation trade-off. So the exploration is efficiently done via classical optimization, and the exploitation via an a sampler that is as efficient as possible. And this localized sampling then importantly avoids the full complexity of this potentially singular degenerate posterior surface, and does not require the sampler to explore the full complex terrain, but actually focus on a localized sampling, which is then easy to accomplish and also much more efficient in terms of runtime. And also then looking at this from a practical standpoint, what would happen if we would actually route the optimization, and looking at some of the best samplers that are out there, like HMC nuts and MCLMC, if you would just not use the optimization, the proportion of meaningful samples and meaningful is in this case not even better than a linear model, which is of course totally useless for this case. The proportions are actually quite low. So this to me looks like a highly inefficient routine if only 3% of my chains would actually result into samples that are useful and meaningful in any way, not even saying that these are really good chains. But just using the simple trick of using high quality warm starts through empirical risk minimization just gives you, it completely eliminates this problem. Like you don't face this problem at all anymore. So this optimization component is pretty critical to boost the effectiveness of these methods. And what I should say that also in terms of budget, this does not really, if you just assign a lot more budget to HMC, NUTS, MCLMC, this will not really recover it in any reasonable budget. So for these proportions, we even used a much higher budget than for the opt plus sampling part and also all the results that we showed before, just to show that basically even a lot of budget will not help you getting rid of this degeneracy. So taking it, kind of summarizing this whole pipeline, we can see that it's basically a transition from maximum likelihood estimation to sampling. And we got three phases. We got first the optimization. And in this plot, what you basically can see is that on the x-axis, you see time. And please don't be afraid of the large runtimes. This is NUTS based. So this is not MCLMC. And on the y-axis, we see again the test LPPD. And we can see that optimization obviously improves the LPPD, so this works and gets to a certain level. But then we take it from there, we do the warm-up. For instance, here for NUTS, it would be a window adoption scheme like in STAN, where we tune the step size and the mass matrix. And then the sampling is done via NUTS sampling as well. So basically HMC all the way. And you can see that this boosts the uncertainty quantification performance significantly beyond this pure optimization level. So each of these phases contributes something to this. And you can also see that there's kind of a trend that the better your optimization, also the better your sampling can get. So basically it's good to invest optimization or to improve methods in each of these phases, right? To basically get the best possible result afterwards. And yeah, with that, I will actually hand it over back to David for a discussion of the implications of these three ingredients that we just discussed: over parameterization, sampling, and optimization.
Yeah, thank you, Emanuel and Julius, for introducing all of this. So now we have I want to show you some implications when we use this approach that we're promoting, that Emanuel was promoting before, combining optimization and sampling. And we'll start off with the priors. So what does it mean in terms of the priors? What did we find? What have we found? What are priors that work well, and what are priors that maybe that we suggest for sampling. And the first result is, so we did a lot of benchmark studies over the last 2 years, and we found that, I mean, something that relates to what you just said, there might be this prior conformity. So we might see that due to overparameterization, things center around 0. And so this plot here shows what are the performances of different priors if you use a Gaussian with a zero centered and at different scales. And you see that 0.5 or 1 seems to be across different data sets, different number of parameters. So that means different network architectures seems to perform quite well. The point here is also that in particular, it performs well if you increase parameter sizes. So it works for 200, it works for 1000. The very same scale, which is sort of different from what you see. Usually people try to get this Gaussian process limit by scaling the variance accordingly to the size of the network. So effectively what we get here is that we get some self regulating effect. So the more we increase the network, the more this scale, this prior, that the variance should regulate the network. And but then we have a larger network that actually is more expressive. So somehow this balances out. Yeah, I think this, yeah. So this is what the sentence on the bottom said. So what are what are the implications in terms of symmetry? Because we said in the beginning, symmetries could potentially hurt the sampling. And now that we have overparameterized the network, is there still, or how much is the influence of these usually seen as these symmetries that are seen as a problematic thing for sampling, like permutation symmetries, scaling, rescaling symmetries, hidden symmetries? Do they actually influence the sampler? And we made a couple of experiments. I'm showing you just one here for the sake of time, where we investigated whether permutation symmetries are really something that could hurt the sampling. And how we did this is that we have this comparison between, like, see here, two plots. And the left plot says it's permuted Wormstads. What that means is that we use one solution, one neural network optimized solution, like a deep ensemble member, one member, and we permuted the neurons such that you get again like functionally equivalent neural network, but now in a different space of the weight space, but they are functionally equivalent. And then you start sampling, and you see that over the different samples, this is the x-axis, you have an increase in the cumulative LPPD. So apparently, the more you sample, the better your model gets. And then the ensemble, the red line, also improves. And if you now compare this to the regular Wormstad, meaning that you take so every of these blue lines is now an individual chain started from somewhere else, not from a functionally equivalent starting point. You see a very similar effect, meaning that it might actually be as effective to start your sampling in functionally equivalent solutions, only have one solution and then permute them, and then run sampling, versus running sampling from 10, 12, you name it, different solutions. And this suggests that there's not so much harmfulness in the permit, or there might actually not be permutation symmetries might actually not be a problem once we do the sampling. Yeah. Then what does now that we have done have this sampling routine in place that can provide samples quite efficiently, we looked into what happens if we now scale this up. If we sample a lot, we use a lot of chains, 100, 1000 chains, and many samples. What do Bayesian posteriors really look like? And of course, this depends on the parameterization and the prior. But what we're arguing before, what Julius was showing, is that there should be maybe this prior pull, this conformity to the prior. So the question is, does everything then turn into a Gaussian because of this overvisualization? And the answer is sort of. You see here a couple of fancy plots, and in the first column is the kernel of different layers. The different layers are the different columns. So first column is first layer, then the second to fourth column is early hidden layer, mid hidden layer, late hidden layer, and the last column is the last layer. And the second row, you see the bias, the distribution of the bias term. Again, these are these marginal plots that Julius was introducing before. And in the hidden layers, you see this behavior that also Julius was showing, that at least looking from this marginal window point of view, you see that things are zero-centered, at least for the kernels, and look very like a Gaussian distribution. At least from this margin perspective, you need to be, take this with a bit of caution. It's just marginalizing over all the dimensions, but we don't see the symmetry patterns here that you saw in the other plot that Julius was showing, meaning that if there seem to be no barriers, like in the underparameterized case. But what we also see here is that there are very distinctive patterns in the first and the last layer, which makes sense because in the first layer you need to learn learn your features from the input data, and then in the last layer you combine them. And then it's not surprising, for example, that the bias term in the last layer has a very narrow specific effect because it essentially represents the mean of your output value. Right. Then another implication, because Emanuel was presenting you this sampling approach, which is great, and it works quite well in these high dimensions. But because we're in these high dimensions, everything is an approximation, right? So even if you have the best sampler, you need to sample a 1 million dimensional space, and if you do this with a finite amount of samples, it will lead to some approximation. So these, no matter what sampler you use, it will be an approximation. And now what we think is very interesting is that there are different types of approximation that we see. So there is in particular what we call a sampler-induced regularization, because the samplers not only differ in their efficiency, but also in the way they approximate this high-dimensional space. And this is a plot showing you some of the results of different samplers in terms of their activation rate. So we looked into ReLU neural networks and then looked into different layers of these ReLU neural networks. This is the x-axis here in the different plots, and the different plots are just different neural networks. You can focus on one plot. And in these different layers, so what layer 1, layer 2, layer 3, we looked into activation rates. So what is the proportion the ReLU activation actually is non-zero. And for the map solution, this is the red one, you see that it's roughly constant across layers. The same also is the case for the BDE, so the nuts-based solutions. So if you sample with nuts, maybe it decreases a bit, but this is not significantly less than the map. But then if you look into what you actually get as activation rates from the MCLMC-based sampler that Emanuel was promoting, you see that the activation rates actually drop quite drastically across layers. So it seems that the sampler prefers sparse and sparser solutions the further you are into the neural network, which is interesting because it's again, as Emanuel said before, nuts and MCLMC based results were usually on par. Maybe MILE or MCLMC was a bit better, but if you say they are almost the same in terms of performance that you get in the end, it's quite interesting that they differ so much in like how much they activate the neural network, what you get as activation rates. So there seems to be like an approximation that is sort of maybe favoring sparser prediction, sparser solutions for MCLMC. Okay. With that, I want to briefly talk about current bottlenecks that we have, the things that we are currently working on. The current bottlenecks that you usually think of is large scale data sets and large models. Large models is something that we sort of address because the sampling routine that we propose is you can scale quite well to high dimensions. Large scale data sets is something that I think is also can be addressed with stochastic approaches. There's also other things, something that we're currently looking into. One thing that is usually overlooked in terms of bottlenecks is next slide. The next point is inference cost. What is different from like the typical optimization routines is that if you do sampling, you produce hundreds, thousands, 10,000s of these weight vectors, and these weight vectors are not small, right? So these are these 1 million dimensional objects, and you need to be able to store these 10,000 copies of one-dimensional vector somewhere, and also you need to process them for inference. So every time you do prediction, you might want to do this Bayesian ensemble, which means that you need to forward pass 10,000 weight vectors of size of 1 million, for example. So this is something that is certainly a bottleneck that approaches that are not sampling based do not have. Right. So let's summarize. We talked about or maybe what we talked about sampling and what is usually considered or the perception in the community is maybe something that also relates to this famous paper by Andrew Wilson and his group, where they try to understand how the posterior looks, what the posterior Bayesian posterior really look like. That was the title. And they write in their paper that to be able to scale HMC to modern architectures and datasets, they needed to parallelize the computation over 512 TPUs. So quite a lot. And what we argue is that actually you can do that much faster and with less compute. So something maybe in the next year or the year after, we hope that what they did takes a day to run on your laptop, and you don't need the 512 TPUs, and you also don't need the time that was spent for their experiments. The ingredients for this, for being able to do this, hopefully in the future, something that you saw today. That was the next point. So what changed in comparison to what maybe Andrew's group did back then? They also used JAGs, but the software that we use is based on black checks. So we haven't talked about that. So we did put quite some effort into getting developing efficient software. The methodology is something that Emanuel presented, or also actually all of us presented. We have this Bayesian deep ensemble idea where you first do an optimization, and then from there you start sampling, and this seems to be quite efficient and effective. Then we have efficient sampling, which is this MCLMC approach that allows us to be ideally even independent of dimensions. And something that we also didn't talk about is that MILE, this MC-LMC based approach that we're using, that Emanuel was proposing in his iClear paper this year, doesn't really need any tuning or not much tuning. It's quite robust towards it in terms of its parameters. So that also saves a lot of time if you don't need to fiddle around with the hyperparameters, right? And yeah, so this was what changed so that we can actually get to these nice results that we saw before. So the lessons learned from this talk hopefully were that that you can that overparameterization can help. This is what Julius was talking about. That this sort of gives you implicit regularization through the prior, the architecture to use, and also maybe the sampler, and that symmetries are not a deal breaker. That would actually be the next slide, but I think the guys, yeah. Right. With that, we're at the end of the talk. Thank you very much for your attention, and yeah, happy to discuss.